Let's now take a look at the Ito formula, which is the generalization of the chain rule in ordinary calculus. Start by considering the following stochastic integral. So we are integrating beta of t, which is the Brownian motion, over d beta t, which is a stochastic integral of beta t over beta. Let's now assume that this beta t is a standard Brownian motion, with q is equal to 1. Now, if you think hard, then based on the ordinary calculus, we would expect the result to be beta squared t over 2. Because if you differentiate beta squared over 2, you will get beta times delta beta. And the integral is obtained once you put in the integral sign. But it turns out to be wrong. The derivation of this result requires us to consider the limiting procedure of the integral, which roughly goes like this. So the integral of beta t db is defined to be the limit of beta evaluated at tk times the increment of betas, which is beta evaluated at tk plus 1 minus beta evaluated at tk. Now, if we rearrange the terms a bit, we can rewrite the terms in the sum like this. So we have half times beta at tk plus 1 minus beta at tk squared plus them half times beta squared at tk plus 1 minus beta squared at tk. We now have this kind of limits. So for the first limit, we notice that the beta tk plus 1 minus beta tk, when the delta t is very small, this is practically equal to delta t. You recall that the increment of a Brownian motion was normally distributed with zero mean and the variance delta t. And in mean squared sense, each of these terms is equal to dt, and the summation of them gives t, and in the end we have minus half times t. For the second term, we notice that this is practically the summation of increments of beta squared. And almost all the terms cancel except for the first and the last, so that the value of this limit should be half times beta squared, evaluated at t. Thus we get this slightly unexpected result. So the integral of beta t d beta t should be equal to minus half times t plus half times beta squared. Of course, the unexpected part is the minus half times t, which shouldn't classically be there. And that's something related to Ito rule that we will see later. And actually the Ito rule is also related to chain rule, and it turns out that this result is unexpected only if we believe in the classical chain rule, which would say that the time derivative of half times x squared of t should be equal to time derivative of x times x. But it's not true for a stochastic process x of t. So it's not true also for beta t. Let's now take a look at the Ito formula, which is the formula which is replacing the chain rule in the case of stochastic differential equations. So what it says that if we have an x of t, which is an Ito stochastic process, and then we have a scalar function phi of x and t, then the Ito differential of phi is given by the formula like this. So the increment of phi is equal to the partial derivative of phi with respect to t times dt plus the partial derivatives of the function with respect to x variables times dx's of the corresponding dimension plus half times the sum of the second derivatives of phi with respect to x's times dxi dxj. And we can also rewrite this as, well, the time derivative of phi with respect to t dt plus the gradient, which is a column vector in this notation, times the vector of dx plus half times the trace of the matrix of second derivatives of phi times dx transpose. Now, in this formula we still have dx's of second order. So how we should proceed in those is that we should use these rules for simplifying them. So dB, dt terms should be set to 0, dt, dB, I mean beta terms should be 0, but the d beta transpose terms should be set to q times dt. Now the extraordinary thing in this formula is that instead of having only first order derivatives and differentials, we have second order derivatives and differentials here as well. Let's now take a look how we can derive the Ito formula. So consider the Taylor series expansion of the function phi. So phi at x plus dx and t plus dt is equal to phi evaluated at x and t plus the partial derivative of phi with respect to time times dt plus then partial derivatives of phi with respect to each of the x's times the corresponding dx's plus half times the second partial derivatives of phi with respect to the xi, xj, and then times the corresponding dx's. We could also add more terms on the right hand side, but it turns out that we don't need more of them. So to the first order in dt and second order in dx, we have the following. So the increment of phi is equal to, by definition, phi x plus dx, t plus dt minus phi x and t. So it's approximately up to first order in dt and second order in dx equal to the partial derivative of phi with respect to t times dt plus the partial derivatives with respect to each of the x's times dx's plus half times the second partial derivatives. And this is exactly the term which is appearing in Ito formula. In deterministic case, we could have ignored the second order term altogether, because when you multiply classical or deterministic differentials together, you will get so small numbers that they just vanish when you take the limit of dt going to 0. But in stochastic case, we actually know that dx transpose is not going to vanish, because it's going to be order dt, because d beta transpose is also order of dt. Let's now take a look at an example application of the Ito formula to the function phi of x is equal to half times x squared. And we will choose the process x to be a standard Brownian motion beta of t. So we are actually computing the Ito differential of beta squared over 2. So in this case, time partial derivative of phi is equal to 0, so we don't have any dt term there. But the derivative of phi with respect to x is equal to x, and when we substitute beta for x, we'll get the term beta times delta beta. Then the second derivative of phi is equal to 1, so we will get half times 1 times delta beta squared. Now in the second line, we will still have the same term beta times delta beta, but then the delta beta squared, as shown on the right, is equal to dt, so the last term is half times dt. And now the result is what we would expect from the previous slides, because we recall that the integral of beta d beta was equal to minus half times t plus half times beta squared, which is exactly what we get from this expression once we put back the beta squared over 2 and integrate from 0 to t. Let's then take a look at another example of Ito formula use. So assume that our x of t is not a Brownian motion, but it's actually a solution to this scalar SDE, which is given by dx is equal to f of x dt plus d beta. Well, now this beta of t is a Brownian motion with diffusion constant q. And we are now computing the interdifferential of the sinusoidal of omega x of t, where this omega is a positive parameter. Then the Ito differential of our sinusoidal of omega x is given like this. So again, the explicit time derivative of sinusoidal of omega x is 0, so we will proceed to the next term, where we have the derivative of the sinusoidal of x with respect to x, which is equal to omega cosine omega x. So that's the first coefficient times dx. Then we have the second derivative of sinusoidal of omega x, which is minus omega squared sinusoidal omega x. So the next term is minus half omega squared sinusoidal omega x times dx squared. And now what we next do is that we take the original dx from above and substitute on the right hand side to this equation. So the first term will become omega cosine omega x times the fx dt plus d beta. And for the second term, we also do the same, so it will become half times omega squared sinusoidal omega x, then f of x dt d beta and the whole thing squared. And now we can go back to the previous slide and recall the rules for dt's and d betas. So d beta dt should be 0, dt d beta should be 0, and d beta squared should be dt. So we notice that actually for f of x dt plus d beta square, the whole thing squared term, we will have some terms dt squared, which are 0. Then we have dt d beta terms which are 0 as well, and the only thing which is left is the d beta squared. So we will have that the last term actually is equal to q times dt. So the final expression is given below here.